Which falls faster? A feather or a brick? Right? Now, everyday experience would tell us that, of course, the brick falls the fastest. If I release a feather and a brick at the exact same time, so if this is my feather, and here's a brick, and I let them drop at the exact same time so that they fall this way and hit the ground, we know that the brick hits first. And that led, this observation, and many others like it, led one of the ancient Greek philosophers, named Aristotle, to propose the idea that heavier objects fell faster than lighter ones. And this can be summed up in a more scientific statement in the form of a hypothesis, in that the time an object, maybe this way, the time that elapses for an object to fall from a certain height is directly proportional to its weight. Okay, so the heavier the object, the faster it falls. And this went undisputed, more or less, for almost 1,500 years or so, maybe even closer to about 2,000 years, until a man by the name of Galileo Galilei came along, and he proposed, actually I think I misspelled that, I think it's supposed to be E-I. Galileo Galilei came along and more or less overthrew the Aristotelian system. We won't go into the entire background as to how this happened, but I will tell you that for as far as Aristotle was concerned, right? So if we go back to Aristotle, his thought process was that thought experiments were sufficient. For true inquiry. In other words, what this means is that if I want to investigate a phenomenon, then all I have to do is think about it, and what makes sense in my mind about what should happen actually is the way it will be. And because we observe heavier objects to fall faster than lighter objects, I don't really have to go out and experiment any more than what my common sense would tell me, and what my mind would conclude as a result of seeing these basic experiments. Galileo, on the other hand, for those of you who are familiar with the whole Missouri joke, the show me state, Galileo was from Missouri, and he wanted to show things through explicit demonstration, not just thought experiments, but true actual experiments. And more than anybody else, Galileo is considered to be the father of the modern scientific method, right? The idea that experimentation is what is necessary. And Galileo did a number of experiments with falling objects, and whether or not this actually happened, it's a great story, but it very likely did. One of the stories is that Galileo went up to the Leaning Tower of Pisa. Hope you enjoy my artwork here. So here's the Leaning Tower, and here's a balcony And Galileo dropped different objects off the ledge, and they would fall, and he would time how long it took them to fall, or he would drop two objects simultaneously and see which ones hit the ground first. And he did notice that feathers let me redo that. That's a bit messy. So feathers, if feathers versus bricks, or rocks or cannonballs, if you will, we'll say rocks. If it was feathers versus rocks, then the rocks would win, right? The rocks would win. But when he dropped objects, heavier objects of different sizes and of different weights, things like maybe a small rock versus a large rock, they both hit at the same time. And he did this with other objects like cannonballs and whatnot. He dropped a bunch of objects, and he even rolled objects down hills to see how varying gravity would work. And his conclusion was that all objects fall at the same rate, the difference is that for things like feathers or a piece of paper or whatnot, the lighter objects are more susceptible or more likely to be affected by air resistance. Okay? Lighter objects are more likely to be affected by air resistance. And this was the beginning of modern physics as we know it. It really was. If you really want to get down to it, you could say that Copernicus overthrowing geocentrism was the true birth, but this was the birth of physical science, right? Experimentation and using observations to determine how nature works, right? And so Galileo concluded that all objects left to themselves, if they were in a vacuum, would fall at the same rate. And we've done this numerous times now, where we have, in fact, vacuum chambered a place out and then dropped two objects and they fall simultaneously. So we know for sure that Galileo was absolutely correct. But that brings up a very interesting question, right? What is that rate? What is the rate at which things fall, right? So what is the rate at which objects fall? An equivalent question would be at what's the rate at which objects are accelerated toward the Earth? Right, so what is that rate? And it turns out that you can do this at home. You can actually measure this at home. And whether or not you realize it, you already have the necessary equations. So if you want to find out what the acceleration due to gravity is, okay, this would be a nice experiment to do at home. Right, so here's your living room floor. If you get a meter stick or some sort of measuring tape or whatever and measure up maybe about 5 or 6 feet off the ground, and drop an object. Not something too big, like a heavy book or something, but something that's a little bit bigger, so it's not going to be affected by air resistance. Maybe a tennis ball would be just about perfect. And get a stopwatch. And then, so here's your tennis ball. It's at 6 feet, and you let it go, and so it falls. And you start your stopwatch right when you let it go, and you time how long it takes for it to hit the ground. And we know from the previous chapter that distance, when the initial velocity is 0, which it is because you're letting it go from rest, is going to be 1/2 at squared. So if the distance is 6 feet and the time is measured in seconds, you can solve for a, right? We did this last time. So if I multiply both sides by 2 and then divide by t squared, I'm going to get a is equal to 2d over t squared. And you can figure out what the acceleration due to Earth is. Now, what is that number that's the accepted number? Well, it turns out that if you do that at home, you should get something very close to 32 feet per second squared. Okay? So, if an object is dropped from rest, what this means is that after 1 second, its velocity is going to be 32 feet per second. After 2 seconds, it'll be 64 feet per second, and so on and so forth. If we do this in SI units, but most people around their house don't have meter sticks, you're more likely to have a ruler or a yardstick or something like that, or a measuring tape. But if you actually do this experiment with a meter stick or with some sort of measuring device that measures SI units, meters, you should come up with a value that's very close to 10 meters per second squared. Okay, the official value of Earth's acceleration, which we denote by little g, okay, so anytime in this course you see little g, it means Earth's acceleration, is 9.81 meters per second squared. Okay? But for our purposes, that's close enough to 10 that for just about everything we do, 10 will be sufficient for your calculations. Right? So, now that we have that under our belt, I'll leave I'll leave you guys with that for now, and then in the next section we'll talk about dropping objects out of buildings and how to determine times, distances, and velocities, and then we'll talk about the situation where we throw an object up into the air and what happens then, and then we will finish up with actual projectile motion, talking about something like maybe a bullet's trajectory or the trajectory of a basketball, and the physics involved with those. So I will see you next time, and have a great one. Thanks. Bye.